Good afternoon, and first greetings to my mentors and professors. In chief, Dr. Donald Schilling, Professor Emeritus of City College, Department of Electrical Engineering. Professors Norman Scheiber, Joe Barber, and Tarek Sidawi, also from the City College, this is University of New York. Today I am in the capital, Washington, D.C., at the Hyatt Hotel. It's close to New Jersey Avenue, or on New Jersey Avenue rather. Formerly, a couple of days ago, I was in Los Angeles, California at Sunburst, where I did a series of short lectures. But today, as I'm saying, I'm at the capital, Washington, D.C. Now, I would like to present new developments on my PDM discovery, new insights, new applications. But before I do that, I'm gonna somehow leave that for the last. I want to just do some brief review on some fundamental engineering topics. The Fourier transform. I'll do a couple of short problems. Fourier transform, a couple of short problems, and some amplifiers. Power amplifiers, class A, class B, class C amplifiers. And finally, I would come to my PDM, HDM application development and forecast for the future. So let me first start off, by doing my review. Fourier transform. My name is Dolphy Gilpin. And now the Fourier transform, and in particular, we did a couple of problems at Sunburst. Today we're doing the signum function. Fourier transform. And the signum function, yes. Like so. We have 0 here, we have 1. This is minus 1. And so we should find the Fourier transform of the signum function. Write it here, the Fourier transform of f of t. Where f of t is equal to the signum function so we see that the Fourier transform is equal now to of double, which is equal now to the Fourier transform f of t, and it's equal now to pi delta omega plus 1 over j omega. Now the lighting is not too lovely here. I'm going to turn on another light, but maybe it might be too much light. Let's see if it's a better lighting here. So we see now that the Fourier transform, notice I have two different symbols for it. Sometimes it's written like so, and sometimes it's written like so. Signal t minus u of minus w. That's equal to pi delta omega plus 1 over j omega minus pi delta omega minus or plus 1 over j omega minus. And if we do the maths and open the brackets, we find out that it's equal to 2 over j omega. So that's the Fourier transform of the signum function, f of t. If we let it equal u of w equal f of Fourier transform of f of t, it will be equal to pi sigma omega plus 1 over j omega. And so we write this now as u of w minus u of minus w. And since we know the Fourier transform of u of w, we have pi sigma omega plus 1 over j omega. And then for the minus, we have 1 over minus pi sigma minus omega or plus 1 over minus j omega. And if we remove the bracket and do the additions and subtraction, we have 2 over j omega. Now we could do this in other way by applying the formula that the Fourier transform of a function is equal to the function times e to the minus j omega integrated between minus infinity and infinity. But we have done it this way. All right, so that's one. Let's do another. I will do the inverse Fourier transform now. This one is going to be relatively lengthier. Try to find a shorter one that could hold on the paper first before I attempt the lengthy one. I say obtain the inverse Fourier transform of the inverse. Let's draw a line under this one. We want now the inverse Fourier transform. function given now would be f of omega is equal to ten j omega plus 4 over j omega squared plus 6 j omega plus 8. So that's the function we wish to find the Fourier transform for. Alright, we'll have to put up another sheet here. So let's just take a break while I lengthen the paper to find the inverse Fourier transform of f of omega equal 10 j omega plus 4 over j omega squared plus 6 j omega plus 8. Okay, good afternoon once more, and I'm coming to you once more from Washington, D.C., the capital, at the Hyatt Hotel, New Jersey Avenue. And I just had a break from the Fourier transform. We will find the inverse Fourier transform of a certain function. And the screen was too short, and so we had to lengthen the screen to contain the problem. So let's start from where we had left off. So yeah, once again, Dolphy Gilpin, your instructor. And we right now that we wish to find the inverse Fourier transform given f of omega is equal to 10 j omega plus 4 over j omega squared plus 6 j omega plus 8. I would say to avoid working in the complex domain, complex algebra with the j's, we replace j omega by s. Make it easier. And then we will, at the end, replace the s by j omega. So what we'll have, we replace that by s. We have now 10s plus 4 over s squared plus 6s plus 8. And we factorize, we have 10s plus 4 over s plus 4 into s plus 2. And we factorize the bottom. And we apply the partial fraction methodology. And we'll have now this equivalent to a over s plus 4 plus b over s plus 2. Yes, we're in the process of finding the inverse Fourier transform of the function f of omega equals 10 j omega plus 4. All right, so we go to the method of finding the partial fraction A and B by multiplying over here by the LCM, s plus 4 to s plus 2, multiply right and left hand side, simplify the algebraic thing, equate coefficients of s squared, s, and constant term, and we get some equation. We solve the equation and we get A is equal to 18 and B is equal to minus 8. Yeah, we're not concerned. You can always do the partial fraction by the partial fraction method, find A and B. This is going to take up too much space here on this thing. So we do it, right, by equating coefficient after we have multiplied through by the SCM, by the LCM, s plus 4 to s plus 2. And we get some two equations and we solve. And we get A equals 18, and B is equal to minus 8. So now that what we have now is that this expression turns out now to be A, which is now 18 over s plus 4 plus minus 8 over s plus 2. And so we have some tables for this. We could look it up. We'll let the table help us. And what we'll get now, if we replace back s equals j omega and substitute A equals 18 and B equals minus 8, that f of t now will be equal to 18 e to the minus 40 plus minus 8 e to the minus 2t. So this is really 18 e to the minus 40 minus 8e to the minus 2t. And now we add a function now, unit step function u of t. So that's our solution now for the inverse Fourier transform. So what we did, we moved from now the frequency domain back into the time domain. And we're finding the Fourier transform, we move from the time domain into the frequency domain. So the second one, we used to find inverse Fourier transform now given. The inverse Fourier transform given now f of omega is equal to omega squared plus 9 rather omega squared plus 21 over omega squared plus 9. So that's the original problem. We have the f of omega is equal to omega squared plus 21 over omega squared plus 9. And so what we did, this is the original problem. We simplify this. And so this is equal now. It looks like from the portion of this, we could get, all right, what I spot here right away, we could say this is equal to omega squared plus 9 over omega squared plus 9, and it leaves 9. Yeah, it leaves 9 over omega squared plus 9. But it leaves 12. Because this is 21, right? So we subtract 9 from 21, 12. So this is equal now to 1 plus 12 over omega squared plus 9. With the help of the table, or if we wish to do this, we could say that's equal to plus 3 factorial times 2 over omega squared plus 3 squared. And recognition of that now, we say that's equal to, Fourier transform of that would be of 1, the inverse Fourier transform of 1 would be L of t plus now 2e to the minus 3t. So there we have it now, the Fourier transform, the inverse Fourier transform of omega squared plus 21 over omega squared plus 9. Well, this is a rather lengthy one here, but we're going to try to accommodate it. Third one, wish to find the inverse Fourier transform of now 6 into 3 plus j2 omega over 1 plus j omega into 4 plus j omega into 2 plus j omega. We have to do some adjustment to our screen again. So let me just roll it up a little bit here. And in continuation now, we say now that we write the function in terms of S, trying to avoid the complex j omega, which makes the algebra a little bit more complicated. So we say now that the function now is 6 into 3 plus 2s over 1 plus s into 4 plus s into 2 plus s. And we say no, that's equivalent to a upon 1 plus s plus b upon 4 plus s plus c upon 2 plus S. So we're going to do the partial fraction methodology there. We multiply this LCM by every term here and also multiply it by that. So we get a term over here equal to 6 plus 3 plus 2S. And then we simplify, equate coefficient of S squared, S and constant term, and we get now that A is equal to after doing the algebra, and that we get A is equal to 2, B is equal to minus 5, and C is equal to 3. So we get A equals 2, B equals minus 5, and C equals 3. We have left out the steps of the partial fraction because that is an exercise for you. This is an exercise on the inverse Fourier transform, which includes some algebra and the partial fraction method. So we left that out and you just write down the answer. A equals 2, B equals minus 5, and C equals 3. Take my word for it. Go and solve the 3 equations simultaneously and you will get just that. And so if you get now that, we go back and we say, no, that's equal now, the function now as 2 over 1 plus S plus minus 5 over 4 plus S plus 3 over 2 plus S. And so the function now is h of t. Go back in the time domain now, finding the inverse Fourier transform. You have now h of t is equal to 2e to the minus t minus 5 e to the minus 4t plus 3 e to the minus 2t. And of course we added unit step. So there again we move from now the frequency domain back into the time domain by finding the inverse Fourier transform given the Fourier transform representation in the frequency domain. And this is what it turns out to be. Well, we use a table to help us to sometimes get the time domain from the frequency domain. But those who are experienced can see the pattern and just write down, after we have done the partial fraction and get the equivalent of the constant, we write it down. 2 is the coefficient in all of these, minus 5, and these are the powers now. 1, 1t, 4, 4t, and 2, minus 2t times u of t. So that's the answer to that one. All right, next we're going to do now some power class A amplifiers, class C amplifiers, and find the power, the gain, and so forth. Yeah, once again, we're back here at the capital, Washington, D.C. Approximate time is 7:28. I didn't know if I changed my New York time, but my clock is saying 7:28. We probably supposed to look at some amplifiers, and in particular, we are on the Class C power amplifier. I've drawn the diagram here. I don't know how magnification is. But this is the diagram of our Class C power amplifier. We have an inductor here. We have, and it's 10 to infinity, L10 to infinity. We have another inductor L2 here. That also tends to infinity. And we have the VCC here, voltage CC. Excuse me. We have the voltage BB here, VBB. We have the load resistance here, RL. And this is the current source II. And the capacitance CED tends to infinity. And we call this so the basic Class C power amplifier. And we here have the AC and the DC load line diagram. That's it. That's the AC load line coming down like so. AC load line. We have VCC, where it cuts the x-axis here. We have VC upon RL upon R load, where it cuts the axis here. The ICM axis, the current axis. We have the VCM here. We have the AC load line. We have the slope of the RL to the -1 or 1 over RL. And we have the DC load line, which is the vertical line here shown. And the maximum power dissipation, PC max. So let's go on to our calculations. Having put up the diagram of the Class C power amplifier and the corresponding AC and DC load line. Now, if we give some specifications on this amplifier, it says here that now PC max was equal to 4 watts. This is a rating now. BV BVCO was equal to 40 volts. And now in max, two amps. We said no, let VCC equals 20 volts. What is the maximum value of our load permissible without exceeding IP max equal to 2 amps? What is the maximum value of the R load? So we want RL max. Question sign. Permissible without exceeding IP max equal to 2 amps. So it must be less than IP max equal to 2 amps. Also, what is the peak current possible if one design an amplifier that does not exceed the maximum average power constraint at any instant of time? Now for the solution now, what we have is that from the AC and the DC load line shown, AC and the DC load line, we have now that IC max, that is from the AC and the DC load line, we have now that IC max is equal to VCC over R load. VCC over R load, right? That's equal to IC max. Maximum point is where the AC load line cuts the ICM axis here, right at this point. So it's equal to I is equal to V over R by Kirchhoff law, or V equal IR, I equal V over R, or Ohm's law. Yeah. And so we say now that our load is equal to VCC over IC max, that's equal to 20 over 2 equals 10 ohms. Now for B, if the amplifier is designed so that the average power dissipation curve is never exceeded, then what we'll have is that VCEO ICQ will be equal now to PC max equals 4 watts. Now in this case, if VCQ equals VCC equals 20 volts, and the maximum permissible peak collector current is then, so we're saying with VCEO equals VCC equals 20 volts, and the maximum permissible peak collector current is IC max equals ICQ equals PC max, I equals P over V, over VCC, that's equal now to 4 over 20, that's equal to 0.2 amps. Also note that in this case, our load resistor RL is equal to VCC over ICQ. So RL equals VCC over ICQ. R equals V over I equals VCC was 20 and ICQ is 0.2, so it's 20 over 0.2, and that's equal to 100 ohms. And note that ICM must be decreased sometimes considerably from the value of IC max over 2 if the maximum average power dissipation curve is not to be exceeded. I have to go back to our AC and DC load line, and we see that ICM must be decreased sometimes considerably from the value IC max over 2 if the maximum average power dissipation curve is not to be exceeded. So there we have our Class C power amplifier. We're doing audio frequency linear power amplifier, and specifically this is the Class C power amplifier. And we did a design and we made a calculation of power, load resistance, IC max, ICQ, and we look at the AC and the DC load line, the slope of RL to the minus 1, which is equal to 1 over RL, the AC load line, the DC load line, the maximum ICM, which is VC over RL, and so on. I max equals 2 amps, giving that PVCO equals 40 volts and power CM max equals 4 watts. So we next look at the class B.